Hello, this is Mr. McMurray. We're talking about heat today and thermal energy. Things are going to really heat up now. Whew. We won't even get into whether I'm hot or cold or cool or whatever, but anyhow, you get the idea. Okay, so thermal energy notes. So first of all, what do we talk about heat? What is heat? For a long time, people did not know exactly what heat was. Okay, there was a theory that it was something called phlogiston, for example. And phlogiston was just something that was in the air. Plants and stuff that took in phlogiston could then be burned because they had this phlogiston in them. When things like rocks and stuff that didn't obviously take up phlogiston because they would not burn. Another idea was something called caloric, and caloric was some kind of fluid that was around the air and allowed the air to heat up and stuff. And the idea basically behind both of these is that heat was some kind of matter, that it had mass, that it had substance to it, and basically we've since proved those to be false. Okay, but the idea is that heat has to do with the motion of molecules. One of the first people to come up with that idea was over here. This is Count Rumford, all right, or his name was also Thompson, but he was known as Count Rumford. And his idea, he was watching them drill out a cannon. So they had a cannon, which they started off with the bore of the cannon, which is a solid piece of metal, and then they would bore a hole in it so that the cannonball could be put in it. And to do that, they had to drill, and when they would drill it out, it would have to slow down and stop for a little while, let it cool off because the drill bit would get so hot, and then they would do it again, and then it would cool off, and so forth. And his idea was that heat then perhaps had something to do with obviously friction and things moving, so it has to do with motion. Okay, and the idea of things being in motion. And based on his observations and some other scientists that we're not going to have time to go into all of them, but he came up with what we call the kinetic theory of matter. Okay, these and some other scientists, it took a while over time to get rid of these old ideas, and they came up with what's called kinetic theory of matter. This idea is that the atoms and molecules of all substances are constantly in motion, or constantly moving. Okay, now that was pretty obvious for gases, because we could feel the wind move. You could see water sloshing around in the pond. Obviously it was capable of motion. But what about solids? Solids didn't seem to have that. So basically they said even in atoms that are extremely small, solids, the atoms are usually locked in place fairly rigidly. Okay, so they can't move very much, but they can vibrate, and so they would just kind of vibrate in place. Those little fancy lines there mean, ooh, they're vibrating. Okay, now someone says, but if I feel my desk, do I feel it vibrate? No. One, because the atoms are extremely tiny, so the vibrations are extremely small, and also they're vibrating in opposite directions some of the time, so it kind of cancels each other out. So either way, you're not going to feel a solid object move, but the atoms in it are still moving. The electrons are still swirling around the nucleus and so forth. So there is motion involved. Okay, and so basically the idea is heat has to do with how fast those atoms are moving. Okay, and normally when we think about heat, the main way we measure that is what we call temperature. All right, temperature has to do with how fast the atoms in something are moving. Okay, if you have a piece of ice, for example, the atoms are not moving as fast as they would be in a glass of water. Okay, nor are they moving as freely in the cup of ice because they're fairly rigidly in place. All right. Now, if I have a big thing of water, is every molecule in there going at exactly the same speed? And the correct answer is no. So temperature is actually the average motion, okay, or we could say the average kinetic energy, because that's how fast they're moving, of the atoms / molecules, depending what it's made out of a substance. All right, and so basically when we're measuring the temperature of something, we're measuring how fast the atoms in it are moving. All right, if I take my cup of water over here and I put a thermometer in it, If the water, let's just say it's boiling water, then the water is going to be hotter than the thermometer, and the heat will flow from the hot water into the thermometer until it's going to be the same temperature as the water that is stuck in. Okay, and that means the atoms in the thermometer will have to start moving at the same average speed as the molecules in the water. All right, now they have stronger forces holding them together, so they're not going to become a liquid, they're not going to melt, but they will move faster and faster, and they will basically become hotter, and they will measure that temperature, which causes the mercury or alcohol in the thermometer to rise up to a certain point. Okay. Now, when scientists said, okay, so we have temperature, the average kinetic energy, we need a way to measure that. All right, and we would measure our temperature using a thermometer. All right, but we kind of take for granted that we have thermometers, and everybody knows what a thermometer is, and they're all measured the same. But when they first did this, people would live in different places. All right, and so they had, and they didn't have big factories that could make mass-produced thermometers. So they said, we need a thermometer so that if someone had a blank thermometer, they could make a thermometer that would match the same one that I have. In order to do that, we'd say, okay, hey, I got a blank thermometer here, and I need to be able to take the temperature of something, say ice, and mark that, and I would know what temperature that is. Okay, and then I need something else, like maybe my body temperature, and I could mark that on here, and that way anybody anywhere could mark those two things, and then they could make little marks or whatever to figure out exactly how much something temperature is, and their temperature would be just exactly the same as what I measured. So we need some sort of reference points, okay, that we can make these all the same. Okay, so we need some kind of reference point. All right, and there are two main temperature scales that attempted to do this. Okay, so we have a temperature scale, and they need to have they need to be reproducible. Some kind of a reference point so that two people in different places can have exactly the same thermometer that measures temperature exactly the same way. All right, the idea of 0 to 100 was a common idea. All right, and it turns out the first one that we hear about is Fahrenheit. Now that looks a little spelled funny, but that is a German name, Daniel Fahrenheit, and he came up with the Fahrenheit temperature scale. All right, and he did this 0 to 100, and he said 0 degrees Fahrenheit was going to be the coldest temperature they could make at that time, which would be kind of like if you're making ice cream. If you need to freeze water or the milk and stuff that has water in it in the ice cream, you would stick it in a canister and you would pour salt, water, and ice around it and get it really cold, and it would get cold enough to freeze. And so we're going to call that icy salt water. All right, or brine would be a fancy word for fancy salt water. Okay, and he said that temperature is going to be 0 on his scale. So on the Fahrenheit scale, that would be right down here. Okay, he said that's going to be 0 for Fahrenheit. All right, and he said he's going to make it easy, so he's going to make it 100. So that would make sense. And I'm going to make 100 human body temperature. Okay, so he made right up here at human body temperature, he made that was his 100. Okay, now later they had to do some adjustments and make some changes in the scale, so it turns out that human body temperature now is actually 98.6 degrees Fahrenheit. Okay, but originally he had planned for it to be 100, which makes sense. If you did your temperatures 100 being normal, then you'd be good. All right, now it turns out in this system that water would freeze at 30 degrees Fahrenheit is where water would freeze, and you would have to go up to 212 degrees Fahrenheit to be where water would boil. Okay, and so his scale 0 to 100 was covered this small area of temperature scale from here to here. Okay, and so basically that's kind of what he was looking at from here to here. That's the temperature scale. All right. Now, about the same time, within about 10 or 15 years later, another one was developed, which is called Celsius, after Lord Celsius. And it was also called, especially when I was growing up, it was sometimes called centigrade. Centa means 100. Grade, or little markings or divisions on it, like a graduated cylinder, same word there, has 100 marks from 0 to 100. Well, so did Fahrenheit scale, but that's why this one was called that. It was called centigrade, because it went from 0 to 100. Now, on the Celsius scale, he said, well, water is very common, and so 0 degrees Celsius is going to be the freezing point of water. That's where water freezes, or ice melts, depending if it's warming up or cooling down. And 100 degrees Celsius is going to be the boiling point of water. Okay, the temperature at which water would boil and turn to steam. All right, and everybody has water. Everybody can produce freeze water or make it boil, although technically at this time a lot of people near the equator probably couldn't have. But for the scientists in Europe, that worked pretty good. And so you had these two scales. Now, it's kind of like Apple computers and PC computers. There's not necessarily a matter of, or Android and Apple phones. You could argue about which one's better, and there's good things about one or the other possibly, but they're just two different scales. All right, not like one's preferable. Probably because Celsius was based on water, and water is very common in living things, and worldwide everybody has to have water. Eventually, Celsius was the one that was adapted. All right, now if you look at the scale here, 0 Celsius right here to 100 degrees Celsius is a bigger range. So actually, Fahrenheit degrees are smaller. In fact, it takes about 1.8 degrees Fahrenheit to equal 1 degree Celsius. Okay, so it's almost a 2-to-1 ratio. All right, so 1.8 degrees Fahrenheit would equal 1 Celsius. All right, so a degree Celsius would be a bigger increase in temperature than 1 degree Fahrenheit going up. All right. Now, eventually, when they did the metric system, they used the Celsius. All right, and that's why you'll see that a lot. Although in weather here, we still use Fahrenheit in the United States. One of these days, that may change, but it hasn't yet. We will see. All right. Number 3, the third type, though, is they came up with another type of temperature scale, which was Kelvin. And so I said, why would we need another temperature scale? We already have 2. Well, here's the deal. It turns out that there's really no limit to how hot something can get. Okay, let's just look at a quick graphic here. I don't know if you can see it. Basically, the hottest thing we know is probably the middle of a hydrogen bomb, which is kind of like an atomic bomb, which is about 100 million degrees Kelvin. Okay, the center of the sun is about 20 million degrees Kelvin. Some stars, plasma, surface of the sun is going to be cooler than the center of the sun, so forth. Things on Earth, we can melt iron, a carbon arc lamp, and so forth. Some of these tin, water boiling, so forth, and so on. Okay, there's no limit to how hot something can get. That's the hottest thing we know of, but there may be even higher temperatures, because temperature depends on how fast the atoms move. And as long as they go faster and faster and faster, then they can get hotter and hotter and hotter. And so there's not really any limit on how hot something can get, but there is a limit to how cold something can get. If temperature is how fast the atoms are moving, then the coldest you can get is when the atoms don't move anymore. Okay, now they did some experiments, and they based on how much the atoms slowed down and lowered their temperature, and how it had to do with their volume. They calculated back, and they said, hey, if we go all the way back, we think the lowest temperature you can get is negative 273 degrees Celsius. All right, and we're going to set that as 0 Kelvin. Notice it's not 0 degrees Kelvin, although a lot of times, just out of habit, I will state that. But it's just Kelvin. Just like if you run at so many meters, 100 meters, you don't say 100 degrees meters or something. And since the degrees really doesn't tell us anything, they got rid of it and they just said it's 0 Kelvin. All right. So in Kelvin, there are no degrees. And so there's no degrees. And there is no